Representing enthalpy practice questions. For cellular respiration, for every mole of glucose here that is being burned and reacting with oxygen, it is releasing this much energy on the product side. We can do the same thing for photosynthesis. But photosynthesis for plants, they take in CO2, they take in water, but they also want to take in energy from the sun. So it takes in this much energy. So it's going to be on the reactant side as opposed to the product side. It's endothermic. Next, we have the methodology number 2. Rather than having to worry about placing it on the reactant or product side, you just have to put a delta H value at the very end of the thermochemical equation, and you just have to add the symbol following suit. So if it's a positive value as shown here, we just keep it as positive. Next, we have methodology number 3, delta H photosynthesis. This is the molar enthalpy. So this is the exact opposite of cellular respiration. It's going to be taking in this much energy for every mole of glucose being formed. So it's going to be taking in this much energy. Again, it's staying as positive because it's endothermic per mole of glucose being formed. It's the exact opposite of the cell respiration. Next, we have methodology number 4, the reactants. It's taking in the energy, it's endothermic, and then it's going to be creating the products. So you just find the difference between the products and the reactants. The difference between that is going to be the delta H value. This next question is asking for us to create a balanced thermochemical equation. Well, I've already created the chemical equation for you. We just have to balance it out. As you can see, it's quite balanced. Then we have to add in our delta H. Well, they've told us what it is. The number is negative 925 kilojoules per mole. Do we put it on this side or do we put it on this side? It's a negative value, so it's exothermic, so we have to put it on this side, 925 kilojoules. This next question here is asking for us to write out the thermochemical equation for both the combustion of hydrogen and the decomposition of water vapor. Let's balance it out appropriately. So we're going to put a 2 over here, put a 2 over here, put a 2 over here, put a 2 over here. And as we can see, we have to put a negative 241.8 kilojoules per mole for this one, for the combustion of hydrogen. So it's going to be over here. However, there is 2 moles of hydrogen as opposed to per mole as stated here. So we have to times 2. So this would be 483.6 kilojoules. It will be the same thing over here for the decomposition of water. It's endothermic, so it's going to be on this side too. So it's going to be, 483.6 kilojoules. And then how does the enthalpy change for the combustion of hydrogen compare with the enthalpy change for the decomposition of water vapor? As you can see, negative 241 versus positive 241, they are the same value, but they are of the opposite signs. Last but not least, we have here identify the greater potential energy, the reactants or the products. Well, CaCO3 here is a reactant. It's taking in energy. As you can see, it's taken in, and then it's going to be creating our products. As you can see, the products are greater than the reactants, so the answer is going to be the products.